Okay, so trying to think if there was anything I wanted to bring up before we start. But last day we did polynomial long division. Very fun once you kind of get the hang of it. We could use it today, but I'm gonna keep it nice and simple. Okay. Or at least in my opinion, I guess. Nice and breezy. Just as a heads up, we're not doing sections 3.5 and 3.6. And so section 3.7 is our last section in chapter 3. And so this is our last kind of chapter 3 topic. And because I heard just now that there's a test after us, we won't start anything new today. So we'll just finish this today, and then you can kind of have some time, whatever time is left over. How about that? Nice. Okay. So what is a rational function? A rational function looks like this. P of x over q of x. And so it looks like a fraction. It looks like a fraction. And just as a refresher, P of x is on the top, and so it's called the numerator. I know I've brought this terminology before, but because we're talking about fractions all day today, I think it's worth refreshing. And so the numerator, and on the bottom you have the denominator. So we'll be focusing today on the denominator for the most part, but also talking about the numerator a little bit. How I remember it is the numerator is numero uno, so it goes on top, right? And then the other one is the other one, right? Whatever way you need to remember. I will say that often P of x and Q of x are polynomials. Right? So we worked with polynomials last week, right? And so Q of x are polynomials. So it looks nice and simple, but we're going to have these kind of elaborate looking polynomials in a fraction form. And what we're going to talk about today are some key properties of these functions. And so just as a reminder, if you have a function like 1 over x or 1 over x squared, these are their graphs, right? And what we're going to focus on today are these vertical asymptotes. And so you might remember asymptotes, maybe from high school, right? Where you have these kind of invisible lines that the graph will never ever touch. It'll approach it, but it'll never ever touch it, right? And so where are these vertical asymptotes? Now let's see here. Here we have a vertical asymptote. A vertical asymptote at x equals 0. And same here. Oh, yeah, asymptote. Asymptote. These vertical asymptotes happen where the value of x is not in the domain. And so to find vertical asymptotes, potentially more than one, and I'm going to start abbreviating these VA because it's really annoying to write. But to find vertical asymptotes, we need to find the values of x that are not in the domain. We need to find the values of x that are not in the domain. Let me the page here. Wait. If we look at something simple like 1 over x is technically a polynomial over a polynomial in its most basic form, right? One, it can be considered a polynomial if you wanna stretch it a little bit. But if you consider f of x is 1 over x, we remember that we can't divide by 0, right? So here, note, we can't divide by 0, right? That's our first check-in point for the domain. What's the other check-in point? And we can't take the even root of a negative number, right? And we can't take the even root of a negative number. In this section, we're going to be dealing with polynomials, which means we don't have to worry about the roots so much, right? But they go hand in hand when we're looking for the domain, and so it might be nice to remember that. But our main goal here is that we can't divide by 0, right? And so that's why we have here, right? So x can't be 0, right? If I'm dividing by x, then x can't be 0. So if we look here at our graph of 1 over x, right, we see at x equals 0, it's removed, right? And we get this kind of, I don't know, in my head, it sounds like, as opposed to this one, which would go, different, I guess. 1 over x squared, right? Still x squared can't be 0, right? And so here, if f of x is 1 over x squared, then we know that x squared can't be 0. Now, if I take the square root of both sides, x is the plus minus root of 0, but positive 0, negative 0 are the same, right? And so then at x equals 0, we'll have an asymptote, or I guess we could do x not equal to these things, depending on how you want to approach it. Okay, nice. One thing that I'll mention, but that we're not going to work at so much, is the difference in these behaviors. Notice how the 1 over x, right, goes in opposite directions in my mind, whereas the 1 over x squared, right, because I have an x squared on the bottom, right, they're both on the positive y-axis, and so they're moving up together. Okay, so different behaviors, right? And I just want to introduce some notation. It's really just so that you've seen it, but we're not really going to use it. I know, weird, right? To denote the two different behaviors, of the functions at the asymptote, we can say for f of x equals 1 over x. Oh, you know what? Just gonna add a page. And these lines are huge. Let me see if I can make them more normal. 3 maybe. There. Looks weird on the first page, but whatever. Let me move this down. Sorry. Tried to cram it into one page. I shouldn't have done that. There. So for f of x equal to 1 over x, we can say as x goes to 0, so as x approaches 0, and then our new notation is this kind of raised to the negative. Now, how we read this is x approaches 0 from the left or negative side. So as we're looking at this function here, I'll just copy it. Oops. No, I won't. There. Oops. Copy. Re-highlight that. Paste. So as we're approaching x equals 0 is here, right? So as we're approaching x equals 0, so x is going to 0 from the left, the function itself is heading down to negative infinity. So we say f of x is going to negative infinity. We've seen very, very similar notation before, right? When we talked about the end behavior of a graph. And so now we're just going to talk about it for asymptotes briefly. And kind of by similarity here, as x goes to 0 from the positive side or from the right, then we see that f of x is going to do what? So here now I'm approaching 0, x equals 0 from the right-hand side or from the positive side, then f of x is going to go to positive infinity. As opposed to if we have f of x is 1 over x squared, oops. Hey, there. I'll grab a oh, excuse me. It'd be nicer to see it like this. So now we see we have an asymptote at x equals 0 again, right? And we can say that, okay, as x goes to 0 from the left, or from the negative side, we see that f of x is going to go to positive infinity. And same thing, as x goes to 0 from the right, f of x is still going to go to positive infinity. And as x goes to 0 from the right, f of x is still going to go to positive infinity. Nice. So just introducing this kind of approaching from the left, approaching from the right notation. Okay. I've got add pages for work and we'll do that. But what we want to do is this one. Yeah. Sorry, let me copy and paste. We'll start with A, of course. Hey, crop. We want to find the vertical asymptotes of f of x, which is x squared minus 4, that's a polynomial, divided by x squared minus 7x minus 8, also a polynomial. Right? And so here we have this rational function that we need to work with. What's one of the nice things here is I see a quadratic, right? And so when I see a quadratic, I'm happy because quadratics are nice to work with, right? We can remember the quadratic formula. And I'm not sure if you've explored your calculator. I can't remember exactly how to do it. But your calculator does do the quadratic formula. Where is it? I can't remember, but it might be worth a Google. Because you are allowed to just use your calculator function, right? As long as you tell me, using my calculator, I found these two values, right? Because what's the quadratic formula going to tell me? It's going to tell me the values of x where f of x is equal to 0, right? So x is negative b plus minus the square root of b squared minus 4ac divided by 2a, right? You are allowed to use the calculator function to solve. I really wish I had reviewed how to do that. There's a QR, I feel like it's QF something. You can find it. You can always just do it by hand too, which we will do. All right. And so the quadratic formula says it finds the values of x where f of x is equal to 0. Now this f of x that I'm talking about here is going to be different than this f of x, right? The f of x that I'm talking about is a generic f of x of the quadratic. So we want to find, oh, question? You don't need it. You can just, if you're good at factoring, then you can just do it. Yeah, it's okay. But for me, I'm really bad at factoring. And so I know that there are people out there who don't like factoring. And so I'll give you a quadratic so that you can just do it, right? When I say, are you good at factoring, right? It has to add to -7 and multiply to -8. And so sometimes it's easy, right? You can just see it and you can break it up. But I want to use the quadratic just because it'll always work, and I'll give you a quadratic to work with. Okay. So no, you don't have to use the quadratic formula. Yeah. If you see it, great. Yeah. I always had a hard time with it though. Add to this and multiply to this. Okay. So we want to find the values where the denominator is 0, right? Because that's where we'll have our vertical asymptotes, right? So our vertical asymptotes are where the denominator is 0. So here we go. We want to find where x squared minus 7x minus 8 is 0. X is negative b plus minus the square root of b squared minus 4ac divided by 2a. I'll add a page. -7 plus minus the root of -7 squared. Make sure you put that in brackets, otherwise you'll get a negative. Minus 4 times a, which is 1, times c, which is -8. Divided by 2 times 1. So I get x is 7 plus minus the root of, let's see here, 7 squared minus 4 times -8. I get the root of 81, which is nice, divided by 2. So I get x is 7 plus minus 9 divided by 2. X is 7 minus 9 divided by 2, or 7 plus 9 divided by 2. 7 minus 9 is -2 over 2, and 7 plus 9, 16 divided by 2, so I get x is -1 or 8. I will make a note though. Note, if you are able to factor without the quadratic formula, you are welcome to do that. X squared minus 7x minus 8. What my roots are telling me, right, these values of x, is that when x is -1, I get a 0, and when x is 8, I get a 0. Okay? And so what we can say is therefore x squared minus 7x minus 8 can be rewritten as x plus 1 times x minus 8. Since when x is -1, it has to become 0, right? 0 times anything makes 0. And when x is 8, it has to make 0. 0 times anything makes 0. Okay. And so notice how you kind of change the sign, right? And so if you have an x is -1, then you have to have x plus 1. And if you have +8, then you have to have x minus 8, right, to reflect those changes. Okay. So if you're able to see that, that's cool, that's great, right? They have to add to -7 and multiply to -8, which +1 and -8 do. Okay. Nice. From here, right, or even from here, we see that we have vertical asymptotes at -1 and 8. Of course, if we were given the factored form, it would be really easy to see where these vertical asymptotes are. So here, from the factored form, it is easy to see where the vertical asymptotes are. Yes, are. Right. Or just, it'll always work as long as you have a quadratic, or you can create a quadratic. That's kind of a trick that we use, right? If you have to create a quadratic, you can do that. Okay. Um, but the quadratic formula will give you the zeros. Okay. And so we have vertical asymptotes at x equals -1 and x equals 8. What we're going to do is just look at it in Desmos. Hopefully my Desmos behaves. I think it was x squared minus 4, which I'll put in brackets, divided by x squared minus 7x minus 8. Is it x squared minus 4? We didn't work with it. X squared minus 4. Okay, nice. So here, let me zoom out a little bit. I'll draw a line at x equals -1, so we can see it, and at x equals 8, just so we can convince ourselves that we have these vertical asymptotes here. Oops, screenshot. Yeah. And so just as we found, we have these vertical asymptotes. And although, of course, we could talk about the behavior around the asymptotes, right? As long as you're comfortable with the notation, that's all I was really going for there. We're not going to explore it that deeply, although we could, I guess. Okay. Any questions about that one? Let me crop this up. If we have to find the vertical asymptotes of g of x, now g of x is still a polynomial over a polynomial, right? And so, but it's nice because it's already been factored, right? And so from the factored form, of the denominator, we see that at x equals -1, all right, if I plug in x equals -1 here, then I get -1 plus 1, then the denominator is 0. And at x equals 2, here, 2 minus 2 also makes 0. Doesn't matter what the rest is, anything times 0 is 0. And so we see that at x equals -1 and at x equals 2, the denominator, the denominator is 0. Therefore, we have vertical asymptotes at x equals -1 and, x equals 2. Nice. See if I can pull them up side by side. Can confirm. Want to wrap it up in brackets. 2 times x plus 3 bracket divided by 3 times x plus 1 times x minus 2 bracket. Nice. Now we see that at x equals -1 and at x equals 2, oops, not x sub 2, there, we have these vertical asymptotes, just as we expected. And I'll bring it in. One day I'll have to clear all my photos from here. It's just Desmo screenshots, basically. It'll be easy to do, though. I feel nothing for any of those screenshots. There were some good times, I guess, but. Okay. Questions? What if we have to find the vertical asymptotes of a function like this? X plus 3 over x squared plus 4x plus 3, right? And so, yep, easiest thing might be to try to factor it if you're able to. Or if you're like me and you just want to brute force it, you can use the quadratic formula because I have a quadratic down here in the bottom. Has to add to 4 and multiply it to 3. Pretty breezy stuff, right? If you're okay with factoring, right? And so here could factor, or the quadratic formula will always work. So I'm going to using the, and can I abbreviate this QF, quadratic formula? We'll find the same answer, but if you can see it, it's a lot quicker, obviously. So I get x, and I'm trying to solve where x squared plus 4x plus 3 equals 0. To find where x squared plus 4x plus 3 equals 0, negative b plus minus the square root of b squared minus 4ac divided by 2a. Negative b, negative 4 plus minus the square root of 4 squared minus 4 times 1 times 3 divided by 2 times 1. Negative 4 plus minus, what is it, 16 minus 12? I'll do a small, fine. I was almost gonna skip the square root, but I won't. Negative 4 plus minus 2 divided by 2. So I have x is negative 4 minus 2 divided by 2, or negative 4 plus 2 divided by 2. I should say and, I guess. I get negative 6 divided by 2, and I get negative 2 divided by 2. So x is negative 3 or negative 1. Oh, I skipped a step. Like they should add to 4. They don't, but that's okay. I'd skip to here, thinking that these were the values, or x plus 3 times x plus 1. Those two have to add to 4 and multiply to 3. All right, -3 for x makes a 0, -1 for x makes a 0. Phew. All right, and so if you're able to factor that quickly, that's fine. So we have h of x is x plus 3 divided by x plus 3 times x plus 1. What do you see? That's kind of tempting. Let me just make sure here. You have an x plus 3 divided by x plus 3. These can cancel, right? And so notice we can cancel x plus 3. That's nice. Which takes us to h of x is 1 over x plus 1. But that x plus 3 is still, it should still be in there, right? But canceling, what did the canceling do? It creates a hole, right? So it's not going to be an asymptote anymore because it's kind of gone in a way, okay? But it does create a hole, okay? And so when we are able to cancel in the denominator, we create a hole in the graph. In this case, at x equals -3. So if we had just stuck with the quadratic formula and said, hey, we have an asymptote at x equals -3, without checking back to see if we can cancel, right, with the x plus 3 in the numerator, then we would have missed that we actually just have a hole here. Okay? So what I want to do is show you the graphs of the two. And I think I remember what they were, but I have the original x plus 3 divided by x plus 3 times x plus 1. Or you know what? I'll do the original. X squared plus 4x plus 3. And then I'm going to do the graph of 1 over x plus 1. Okay? What we'll see is that they look the same. Okay? So 1 divided by bracket x plus 1. Going between the two, they overlap. Okay? But here, at x equals -3, let's see if I can show it. X equals -3. I'm trying to show that there's a hole here. Oops, this one. Nope. -3 and undefined. You'll have to, I can't take the screenshot because I'm also using my pencil there. But at x is -3, the function is undefined, telling us that there's a hole there. Let's see if I can. Will it take a screenshot if I do this? Ha, did I catch it? Oh my gosh, the greatest feat there ever was. Okay. Okay, this screenshot I might have to save. Cherish it forever. Crop it up a little bit. So of course, in the graph of 1 over x plus 1, there's no hole, right? Because it doesn't know about the previous x plus 3 that you've canceled. But we did see, we saw the two graphs are identical. Identical. But the original graph has a hole at x equals -3. Nice. So just remember that if you're able to cancel something in the denominator, right, then instead of it being a vertical asymptote, then it creates a hole. Right? So that's the difference. I do have a test question here, but I want to just move these around here. Let's talk about what the horizontal asymptote is. I feel like you'll have lots of time to study for your test. So horizontal asymptotes are on the horizontal axis, right? And so what we'll find is that there are some kind of nice and easy rules for finding the horizontal asymptotes. And so the horizontal asymptote of a rational function, you can look at the degrees. Now that's where it's helpful to remember, okay, these are polynomials and I can find the degree. The degree is the highest power, right? The degrees of the numerator and the denominator, which is why we had to freshen up on that terminology. Now, if the degree of the denominator is larger than the degree of the numerator, right? So you're dividing by something kind of with a higher power than the numerator, then you'll find that there's a horizontal asymptote at y equals 0. Okay, so on the x-axis, there will be a horizontal asymptote. Okay, so as an example, let's look at these here. X over x squared, so I have degree 1 over degree 2, right? If I compare those two, then I have a higher degree in the denominator than the numerator. So then I see that I would have a horizontal asymptote at y equals 0. Now, if we go back to our graph, I'm all zoomed in there at x equals -3. But if I take a proper picture here, right, consider h of x is x plus 3 over x squared. What was it? Plus 4x plus 3 from above. And I'll just bump this. We see that the numerator has degree 1, and the denominator has degree 2, right? And so from here, if the degree in the denominator is higher than the degree in the numerator, we expect a horizontal asymptote at y equals 0. And usually we abbreviate horizontal asymptote as HA, of course, similar to the VA. So we have a horizontal asymptote at y equals 0, which we can see here. Well, nice. So we can talk about the horizontal asymptotes, the vertical asymptotes, the holes. Right? If the degree of the denominator is less than the degree in the numerator, then there's no horizontal asymptote. And so it'll just kind of not steady on any horizontal axis. Whereas if the degree of the denominator is the same as the degree of the numerator, this one's probably the most interesting, then the horizontal asymptote is at the ratio of the leading coefficients, which means we have to dust off that terminology. What's the leading coefficients? It's the coefficients in the leading terms, right? And so you want to make sure that you've written your polynomial in order, right? Decreasing from smallest to largest power, because then you'll be able to pick out the leading coefficients. Let's use the other two. So we've already found the horizontal asymptotes of the last one. I'm going to copy this guy. And clean it up a little bit. Consider the functions from earlier. Find the horizontal asymptotes. So for A, I have x squared over x squared. Right? So here the degrees of the numerator is equal to the degree of the denominator. So I'll do it down here. For A, the degree of the numerator is 2 and the denominator is 2, which means from earlier, let's see, use our crutch. If they're the same, then we have a horizontal asymptote at the ratio of the leading coefficients, which tells us that we have a horizontal asymptote at, very boring, the leading coefficient of x squared is 1 and the leading coefficient of x squared is 1, but that's okay, at 1 over 1, which is at y equals 1. I'll say y equals 1 over 1. Now we've got the graph here of this thing. Let me nab it. Copy. So at y equals 1, looks like I have it here, kind of. I didn't keep the graph, but you'll just have to trust me when I say it's at y equals 1. It does cut through one of those lines, one of those parts of the graph, but that's okay. Long-term behavior is what we're looking at. How about for B? For B, we have, I'll add a page. Keep adding a page. I have a degree 1 in the numerator, right? Highest power of x. And I have degree 2 in the denominator. Which means from my notes here, the degree of the denominator is greater than? Which was it? 1. The numerator is less than the denominator. This one, y equals 0, is where I expect a horizontal asymptote. Let's confirm, in case I mix those up. Maybe it's more clever to do the degree of the denominator first and then the numerator so that you can read them not backwards, but that's up to you. Looks like it is at y equals 0. We do have a horizontal asymptote. Okay. Let's just for fun make up a new one that we haven't seen before. I think if the degree of the denominator is less than the degree of the numerator, just knowing that there's no horizontal asymptote, it's kind of boring, but I do want to show you just a quick one where the degree of the denominator is the same as the degree of the numerator, but maybe with something more spicy in the leading coefficients, right? And so they're going to have the same degrees in the numerator as the denominator, and let's do negative 3x. Well, we don't have to factor this, so let's do x to the 3, why not? Plus 2x minus 4 divided by, let's say 6x to the 3 minus 3x squared plus 2x minus 1. Just completely making stuff up, right? My only goal is to have the same degree in the numerator as the denominator. So here I have the same degree, which means I have a horizontal asymptote at y is equal to negative 3 divided by 6. Can simplify that if you want, but I'll never remember what I just made up. I'll need to bring it up here, but we'll graph it just to see. Negative 3x to the 3, step it down. Oops. Plus 2x minus 4 divided by 6x to the 3, step it down, minus 3x squared plus 2x minus 1. Now what we said is we are going to have an asymptote, a horizontal asymptote at y equals -3 divided by 6. And that seems to be the case. And it will be the case, but just nice to see it, that it works out. Oops. So here we can see that there's a horizontal asymptote. Now, in terms of what to expect for a test question, I want to outline it, and it's in the notes already. But a test question will look like this. I'll give you a rational function, p of x over q of x, okay? And I'm going to ask you to find the vertical asymptotes, okay? I'll make it nice. You'll be able to use the quadratic formula, all right? And so if you're okay with factoring, then that's easier, of course, but you'll always be able to fall back on the quadratic, which is nice. And so you have to find the vertical asymptotes. And are there any holes? If so, where? Right? And so, which means that you'll want to factor the numerator and the denominator, right? Or use the quadratic formula. And if there's any cancellations, right, then that creates a hole instead of a vertical asymptote. And then finally, is there a horizontal asymptote? If so, what is it? Right. And so as you're doing the homework problems for 3.7, right, they'll get you to practice these things individually, but just know that you'll have to just put them into one question, right? And so vertical asymptotes, holes, horizontal asymptotes, and that's it. And if you can believe it, that's the end of chapter 3. The end. Yikes. I promise. So you get to go study for your other tests. I also posted the 3.7 homework if you're interested, but good luck on your test later. And if you have any questions, please let me know. Otherwise, see you Thursday.
Thank you.